Hello and welcome. The topic discussed is air fuel ratio. We will try to find whether 1 kg of petrol, otherwise called as gasoline fuel, requires 15 kg of air to burn completely. So engine is supplied with both fuel and air. Now the question is, what is the amount of air required to burn the fuel? So why is air supplied? So we know that oxygen is required to burn the fuel, and this oxygen is available in the air. Regarding dry air contains 79% of nitrogen and 21% of oxygen. The mole ratio is 79 by 21. It is equal to 3.76. It means that if 1 mole of oxygen is supplied, along with it 3.76 nitrogen mole is also supplied to the engine. So if dry air is supplied, if I supply 1 mole of oxygen, it means that even along with that 1 mole of oxygen, 3.76 mole of nitrogen is supplied to the engine. So the chemical structure for the petrol fuel, the chemical formula for the gasoline fuel is C8H18 and the figure shows the chemical structure. For the air, we have a composition of oxygen and nitrogen, 21% of oxygen and 79% of nitrogen. The combustion equation, we know that equation has left side and right side. This is a reaction, therefore we have reactants in the left side and products in the right side. So here the reactant is the fuel, C8H18. So combustion means conversion of C into CO2 and H into H2O. When C converts to CO2, heat is liberated. When H is converted to H2O, heat is liberated. Therefore, the conversion of C to CO2, H to H2O is combustion. So for this conversion to happen, the fuel requires the air. So both fuel and air is the reactant. Now here the question is, what is the amount of air required for the combustion reaction? So now let us see what are the products. So we know that C has to be converted into CO2. Now we can see that there is 8C in the left side. So because we have 8C, we have to convert all this 8C into 8CO2. So we can see the mass balance here. Correct? So mole balance also we have done here. Okay. So C8 is converted into 8CO2. You can see here C8 and 8C, the mole balancing is done here. Then we have another product which is H2O. H converts into H2O. Correct. So again we will go for the balancing. Here we have H18. Therefore 9H2. 9 into 2 is 18. So again we are balancing the hydrogen moles also. So here we can see C8 converts into 8CO2. H18 converts into 9H2O. Correct. Now in 8CO2, how many oxygen moles are there? We have 8 into 2, 16 O is there. Correct. Similarly, in 9H2O, we have how many oxygen molecules here? It is 9 into 1 equal to 9O. Totally 16O plus 9O is 25O. So therefore, in the air, I must have 25O. So because we are showing in terms of oxygen molecules, we will show as 12.5 O2. So 12.5 into 2 is 25. So we are again balancing the moles here. Okay. So in the air, if I have 12.5 moles of oxygen, that oxygen can convert C8 into 8CO2, H18 into 9H2O. Is it clear? Now, because we are supplying the oxygen, also we will be supplying along with this oxygen nitrogen, because nitrogen is there in the air. So if I supply 1 mole of oxygen, 3.76 moles of nitrogen is supplied to the engine. Here in this case we are supplying 12.5 moles of oxygen. Therefore, we will be additionally sending 12.5 into 3.76 moles of nitrogen into the engine cylinder. The air what we are sending in is 12.5 O2 plus 12.5 into 3.76 nitrogen. Okay. Now, because we are sending the nitrogen inside, it has to also come out. So, the amount of nitrogen moles coming out is 47 N2, that is 12.5 into 3.76 is equal to 47. So, this is the complete reaction. Okay, the combustion equation. So, you can see here C8H18 plus 12.5 O2 plus 47 N2, the reactants, gives 8 CO2 plus 9 H2O plus 47 N2, the products. So here we can see 1 mole of fuel requires 12.5 moles of oxygen, 47 moles of nitrogen, 8 moles of CO2 is given as a product, 9 moles of H2O is given as a product, and the nitrogen comes out, 47 moles of nitrogen comes out. This is the combustion equation. Now let us convert the number of moles to mass, because I want to know what is the kgs of air required for 1 kg of fuel. So let us convert all the moles into number of moles into mass. So this is the reactant, and we must know the molecular weight of different elements. The molecular weight of carbon is 12 grams per mole, hydrogen is 1 grams per mole, oxygen is 32 grams per mole, nitrogen is 12 grams per mole, and the formula to convert the moles into mass is equal to number of moles into molecular weight, and the formula is mass is equal to N into mu. Okay, N means number of moles, mu means molecular weight. So let us now convert the moles to mass. So first we will take the fuel, mass of 1 mole of petrol fuel. Let us find that. So 1 mole of C8H18 is equal to number of moles of carbon into molecular weight of carbon plus number of moles of hydrogen into molecular weight of hydrogen. So let us now calculate. It is equal to 8 moles of carbon into molecular weight of carbon is 12. So 8 into 12 plus number of moles of hydrogen, it is 18 into molecular weight of hydrogen is 1. Therefore, it is equal to 8 into 12 plus 18 into 1. The value is 114 grams of fuel. Okay. So 1 mole of C8H18, the mass is equal to 114 grams. Is it clear? Okay. Now, mass of 1 mole of fuel C8H18 is equal to 114 grams. Let us take it as equation number 1. Now, let us take the mass of air. 12.5 O2 plus 47 N2. What is the mass of this 12.5 O2 plus 47 N2? That is the mass of air supplied. So, it is equal to number of moles of oxygen into molecular weight of oxygen plus number of moles of nitrogen into molecular weight of nitrogen. It is equal to 12.5. Number of moles of oxygen is 12.5 into 32. 32 is the molecular weight of oxygen plus number of moles of nitrogen is 47 into molecular weight of nitrogen is 28. Therefore, it is equal to 12.5 into 32 plus 47 into 28. The value is 1716 gram of air. So, mass of air, that is 12.5 moles of oxygen plus 47 moles of nitrogen required to burn 1 mole of fuel is equal to 1716 grams. Let this be equation number 2. Now we have found the mass of fuel, mass of air. So here mass of 1 mole of fuel C8H18, it is equal to 114 gram. Mass of air is equal to 1716 gram. Now, air fuel ratio is equal to mass of air by mass of fuel. It is equal to mass of air as per the equation number 2 is 1716 grams divided by mass of fuel, it is equal to 114 grams. If you divide this value, it is equal to 15.05. So the air fuel ratio is equal to 15.05. So the air fuel ratio, the value is 15.05. So therefore we can say to burn 1 kg of petrol or otherwise called gasoline fuel requires 15 kg of air to burn completely. So whenever you are asked any questions in IC engines regarding air fuel ratio, be clear that to burn 1 kg of petrol, you require 15 kg of air. In the examination, they will ask you the air fuel ratio of petrol fuel. You must say it is 15:1. Is it clear? Thank you.